This video is part of the series to accompany discrete mathematics and functional programming. I'm Thomas Van Drunen. If you're watching these videos in order, perhaps I should mention that it's actually been 2 years since I made a video on section 1.12. So if the style is a little inconsistent, that's why. Still have the same glasses though. In this video, I will introduce a new and very important family of types called lists. And programming in ML, and more generally programming in the functional style, relies very heavily on processing lists. Lists will also be important for the purposes of this course in how we model mathematical objects. And furthermore, lists will provide a context for talking about and practicing recursion. Let's jump in with some examples. At the basic level, a list is, well, just what it sounds like. It is a sequence of values. And here I am going to have a sequence of integers, ints. You can see that I have separated them with commas and surrounded them with square brackets, terminate the expression with a semicolon, and the ML interpreter identifies this as an int list. I can have a list of reals, and so that is identified as a real list. We could have a list of chars, and if we have a data type, then we can also have a list of the values of this data type. So, and the ML interpreter identifies that as a beverage list. In each of these examples, you can see that the ML interpreter accepts these expressions and infers their type to be a list of whatever the values are. Int list, real list, char list, beverage list. And we can compare this with tuples, which you already know about. So the ML interpreter finds this as a tuple of int by beverage. What lists and tuples have in common is that they are both compound types, or what you could also call them composite types. That just means that these types of values that are composed of smaller pieces. Tuple types and list types are types that are derived from other types. But notice the difference between tuples and lists. With a tuple, you can include values of different types, and the type of the tuple depends on the number of things in the tuple. So a tuple with 2 ints is of a different type from a tuple with 3 ints. And that's different from a tuple with an int and a real. Lists are sequences of uniformly typed values. So you can't mix ints and reals, for example, in the same list. We get an error. The ML interpreter's response might be a little difficult to understand at this point. It might make sense if you review this part of the video after seeing all of it. But the point is that ML will not accept a list with both ints and reals in it. Likewise, the number of elements in a list does not affect the type of that list. So I can have a list with 2 things, and it is an int list. And if I have a list with 5 things in it, it is still an int list. So both of these are int lists, and we refer to int as the base type of this list. There's a lot more that can be said about lists and types, but we'll come back to that. I want to talk a little more about how we define lists. Let's take the analogy of a line or queue of people. Say Betsy, Libby, Liza, Bess, and Buffy are waiting in line at the counter to order lunch. Altogether, the ladies make a line, and Betsy is at the head of the line. We could also say that there is a line behind Betsy, a line that's growing impatient as Betsy tries to decide between curly fries and onion rings. So, Libby, Liza, Bess, and Buffy themselves make a line. Libby is at the head of that line. But on the same token, Libby has a line behind her. Liza, Bess, and Buffy constitute a line on their own. Behind Liza is a line with just Bess and Buffy. And the line behind Bess comprises just Buffy. We can also say there's a line behind Buffy, but that line is empty. If you can accept that way of talking about a line, then we can define lists recursively this way. A list of ints is either an empty list or an int followed by a list of ints. We call that first int the head, and we call the list of ints that follow it the tail. The important thing is that a list is seen as having two parts. The first item in the list is special. It is seen as a part all by itself. Everything else in the list altogether constitutes the other parts. The second part of a list is itself a list. So you can't break a list just anywhere. You can only cut off its head. That is, unless the list is an empty list. Then it has neither head nor tail. It's just an empty list, and that's all we can say. But an empty list is still a list. That in turn brings us to the operations that are defined for lists. Let's store a list in a variable. ML has operations for breaking a list apart into its head and tail. We can write HD for head. The head of XX is 4. We can write TL for tail. The tail of XX is the list that contains 1, 18, and 2. Recall that if we have a tuple, like this one, that we can extract the components of this tuple using #1, for example, or #2. With lists, the head and the tail operation are analogous to that. So notice the types of something like the result of the head of XX. So it is an int, whereas the type of tail XX is an int list. We can keep cutting a list down until we get an empty list. So I'm going to take the tail of XX, and so the list 1, 18, 2 is stored in it. I'm going to take the tail of it. That gives me the list containing 18 and 2. I'm going to take the tail of that it and get the list containing only 2. I'm going to take the tail of that it. That gives me an empty list of ints. It's still an int list. It just doesn't happen to have any ints in it. But if I try to take the tail of that, I get an error because you can't take the tail of an empty list. Let's see, what is it right now? Notice that it is still an empty list. If we take the head of it, we also get an error because you can't take the head of an empty list. These two operations, head and tail, are what I call analytic operations. They are analytic in the sense that we use them to take a list apart. Just as important are the operations we can use to put a list together, to make a new list. These operations, which I would call synthetic operations. We've already seen how to make a list explicitly from scratch. So let's say in variable z, we're going to store 5, 12, 13, 44. Once we have a list, we can make a new list from it by putting on a new head. This double colon operator is called the cons operator because it is used to construct a new list. Notice that the old list hasn't changed. ZZ still has 5, 12, 13, 44. In fact, we can make a new list from scratch simply from repeated applications of the cons operator. So I'm going to call list BB to be 4, cons to 12, cons to 17, cons to 9, cons to an empty list. And that gives me the same thing as if I had simply put 4, 12, 17, and 9, comma delimited between square brackets. From this, you can notice that the cons operator works from right to left. It must have a list on the right and an item on the left. And so this previous example would look like the following if we fully parenthesized it. We would be doing 4 cons to quantity, 12 cons to quantity, 17 cons to quantity, 9 cons to empty list, close paren, close paren, close paren. There is a second synthetic operator, and it differs from cons in that it takes two lists and hooks them together, or concatenates them. It's called the cat operator for short, and we make it using the @ sign. And so I can take our list ZZ and cat it with the list BB, and you see we have a new list containing all the things from list ZZ followed by all the things in the list BB. Note that although the cons operator does not allow you to put an item at the end of a list, I mean, let's try it. If we'd said BB and try to cons 8 after that, we will get an error. The cat operator gives you a workaround if you want to do that. What you can do is simply make the item you want to add to the end of the list to be a list all by itself. So I'm putting square brackets around 8. It's now the list containing 8. And now we can concatenate B with that list containing only 8. And of course, this would actually work if I had used BB instead of just B. I guess I should have thought in Star Wars, BB-8. To summarize the operations on lists, we can extract the head or tail of a list, and we can construct a list from an item and another list, or we can concatenate two lists together into a new list. In practice, the cons operator is the important one. We will very rarely use the analytic operators. Instead, once we start writing functions for lists, we'll find that we can use pattern matching to analyze a list implicitly. The cat operator comes in handy sometimes, but it's not as pure or basic as the cons operator. I want to take a moment now to talk about lists and sets. Just as sets are the most important mathematical concept or object in the math side of this course, lists are the most important way to structure data in the programming side. As you've seen so far, for each math concept that we look at, we're going to talk about ways to model that concept in ML. We already have one way of modeling sets, and that's using a data type. That works because a type, after all, is a set. But data types aren't a perfect way of modeling sets. They don't give us a way, for example, of making subsets or performing set operations. Lists will, in fact, be our primary way of modeling sets. If we want a set of some specific numbers, for example, we can make a list of those numbers, and that will stand for that set. With lists, we'll be able to invent ways of computing the union or intersection and that sort of thing for the sets that the lists are modeling. Lists aren't perfect models of sets, however. First of all, lists are ordered, unlike sets. And second, lists can contain the same item more than once, which doesn't make sense for a set. But we'll find ways to work around these liabilities. But here are a few important things that the connection between lists and sets brings up. First, I hope that you're now comfortable with the difference between a thing and the set containing just that thing. Similarly, the list containing only 5 is a different thing from the value 5. We can see that by the different types that the ML interpreter gives in response to these two different expressions or values. Recall that we can talk about sets of anything. We could even talk about sets of sets. Similarly, a list can contain elements of any other type, as long as they are all of the same type. We can even have lists of lists. Note that the ML interpreter sees this as an int list list, and so reading that type backwards, this is a list of lists of ints. Note that this list of lists can contain an empty list. The last item in this list is a list, though it's an empty list. We can retrieve that empty list by taking the head of, the tail of, the tail of, the tail of this list that we just wrote. Note the difference between that and if we simply took the tail of the list containing 1, 2, 3, and the empty list. That gives us a list containing an empty list. The tail of that would be an empty int list list. Make sure you understand the difference between a list containing an empty list and an empty list of lists. Kind of like the difference between a box containing an empty box and a box intended to contain boxes, but that happens to be empty. Empty lists bring up one more thing about types. You've seen that the ML interpreter can infer the type of a list by its base types, but an empty list doesn't have any components for the interpreter to use for this inference. How does the ML interpreter know the type of an empty list? Well, this most recent empty list is an int list list because it is the tail of a list that contained int lists. The previous empty list, which the ML interpreter finds to be of type int list, was an empty list inside of a list that contained other int lists. So you might need to think carefully about that, but I encourage you to maybe pause the video at this point and see if you can figure out the difference between the empty list that the ML interpreter finds to be of type int list and the empty list that the ML interpreter finds to be of type int list list. The big picture is that the empty lists in these examples could be figured out by context. They appeared in places where one would expect a list of ints or of whatever. But what if we had an empty list with no context at all? What if I simply typed in an empty list right here? The ML interpreter says that this is a list of apostrophe A. Well, here's what that means. The apostrophe A is a type variable. So it's a variable that ranges over types. And this is a bit beyond the scope of what we want to talk about today, but just so you know, in ML, variables can range over types. They can store types. And a variable that ranges over types needs to begin with an apostrophe. What's important for us right now is that this simply means that the ML interpreter is telling us this is a list whose base type it cannot figure out. It does not have enough information to infer what that base type is. We'll see type variables in later sections. What I want you to see now is how to inform the ML interpreter of a type that it can't infer. We use what's called explicit typing. And so I'm going to again input an empty list. What I'm going to do now is put colon, and then I'm going to say int list. And so that looks very much like the response that the ML interpreter gives with the colon and the type. And now the interpreter has the information needed to identify the intended type. You won't need to do this very often, but there will occasionally come up times when our input expressions are complicated enough that the ML interpreter will not have sufficient information to infer the type that's intended. We need to tell it. To test how well you understand lists and types, which I think is a good proxy for how well you understand lists, I recommend working through what I call type analysis problems. It's where we carve a complicated expression into its subexpressions, determine the type of each subexpression, and use that information to synthesize the type of larger and larger expressions until we've discovered and proven the type of the entire expression. Let's take this expression here. We have our answer, of course, from the ML interpreter, but let's see how it is derived. Start with the expression. Identify the smallest subexpressions, the values of primitive type, or literals. We can also identify this empty list. It's basically a literal itself. But let's pretend we can't figure out its type in our heads, and we'll provisionally call it as an unknown type list. The other lists have ints in them, so we know they are int lists. Now we can identify the tuples and infer their types from their components. Since all these tuples must have the same type, since they are in a list together, that context allows us to fill in the unknown type with int. And now we have a demonstration of the type of the entire expression. One final word about lists for those of you who have programmed before in a language that supports arrays, such as C or Java. You probably noticed that lists have some similarity with arrays. Similarity in terms of their purpose, namely as something used to store a sequence of uniformly typed values. But there are important differences between the two. You can read about the differences between lists and arrays in detail in section 2.7 in the book. But the key difference is between what's called sequential access and random access. Lists have sequential access. In order to retrieve something from a list, one needs to step through the list one thing at a time in a sequence. Arrays have random access. That means that you can jump directly to an item in an array by naming its position. It's like the difference between a scroll and a modern book, or codex. You can jump right to a page in a book based on page number. Books have what we call random access. But to get to a place in a scroll, you need, well, to scroll through the entire thing until you get to the place that you're looking for. And that's what lists are like as well. In the big world of computing, lists and arrays, or more generally, sequential access versus random access, have their advantages and their liabilities. For our purposes, lists just are what they are. They're the rules of the game that we're going to play. And next time we're going to learn a little bit more about that game, and we're going to start playing that game. Specifically, what we're going to look at is writing functions that operate on lists. And that's where real list processing, real thinking through lists begins. And in some ways, you could say that writing functions for lists is the primary programming topic of the book.